Okay, in this chapter, chapter 1b, we look at the number systems. Basic introduction to number system, which you have already done. I just want to run through that with you. So the first one is we look at binary to decimal conversion. So if you have a binary number, that's the least significant bit. That's your most significant bit. So if you want to convert this into decimal position, first position is 2 to the 0, the second position is 2 to the 1, third position 2 to the 2, the fourth position is 2 to the 3. So you multiply this one by that, this one by this one by this, and that one with that. Write down the value and add them. So this is equal to, this binary number is equal to 10 in decimal. And then you look at the decimal to binary conversion. So there are many ways of doing decimal to binary conversion. You can divide the number by 2 and keep dividing until you get a remainder. That's one possibility which you have done. The second way of doing it is a bit easier as well. So 25 is a number. We write them as sum of powers of 2. So 16 plus 8 and then 1. That will give you 25. Then you look at the position. So that one goes in there. There's no value here, so that will be 0. No value here, 0. And that's 8, that's the next position. And 16 is the next position. So that's the binary equivalent. So there are examples at the end of the chapter. You can try this out. Now if you look at the binary to decimal table, decimal numbers going from 0 to 9, and the basic numbers are 0 to 9, and we look at the binary, all zeros. This is a 4-bit binary number. All zeros is equal to 0, and this one is equal to 5. You can use this principle to convert them into that. And this one is equal to 8 because that's only 1 in that position. And then this is 9. After that, this one gives you 10, 11, and so on. When you have in a 4-bit binary, if all of them are 1, that gives you 15. So this would be 1 times a 2 to the 0, 1 times a 2 to the 1, 1 times a 2 to the 2, 1 times a 2 to the 3. Add them up, you will get 15. Let's look at the next slide. Decimal to binary equivalence. So whenever you have a binary number which has all ones, then we can find the decimal equivalent in a simpler way. So decimal equivalent is equal to 2 to the power, the number of bits minus 1. So if you look at this table, this is a 2-bit number, all are ones. Therefore the decimal equivalent will be 2 to the 2 minus 1, which is equal to 3. And this is a 4-bit number, and all are ones. So the decimal equivalent is 2 to the power of 4 minus 1 is 15. You take this one is a 12-bit number. So there's all ones, 4, 4, 4. So 12 bits. So the decimal equivalent of that will be 2 to the 12 minus 1, which is 4095. It's handy to have that understanding. When all bits are 1, then the decimal equivalent is 2 to the power of number of bits minus 1. Next one is the hexadecimal notation, or hexadecimal numbers. And hexadecimal numbers start from 0, 1 up to 9, like decimal, and then you have got A, B, C, D, E, F. Altogether there will be 16 values, but 15 the last one will be. So if you look at binary to hexadecimal and look at this table, that 0 is 0, same as its decimal. Up to 9, what we had before will be there. Then 10 decimal is represented by A, in bracket I put the decimal equivalent. 11 is B, and 12 is C, and so on, and 15 is F. So that's your binary to hexadecimal conversion table, and you need to remember this table. When you do questions again and again, you'll remember this pretty fast. If you don't remember, you need to look up this table, but it's not hard to remember this one, and you'll be a lot faster if you remember. Let's look at a hexadecimal number and see how do you convert into binary. So before I go through, let me rub this out for a second. Yep. Now, we've got 8 C F. F is that one. So you say 1, 1, 1, 1. C, and you can see that C is this one, which is 1, 1, 0, 0. And 8, as we know, 1, 0, 0, 8, 1, 0, 1, 0, 0, 0. So 8 is here. That's how you convert a hexadecimal to a binary. Now, how do you convert a binary to hexadecimal? So you've been given a binary number, 11110, which is equivalent to E. And then this is 1010, which is A. So this binary number is equal to AE. So when we are writing the binary number, you would have seen now I'm writing them as a group of 4. Like in a group you have 4 bits there. The reason is the table is also like that. 4 bits, you get one number. 4 bits, you get one number. So if you are given a 16-bit number, you group them as 4, 4, 4, 4. Start from the least significant and move your way up and group them to 4, 4, 4. And then you can convert them into hexadecimal pretty fast. Now, how do we use this? Look at an example. So we are saying a computer memory contains binary instruction and data, and it has got a memory of 65,536 locations. That means we need 16 bits to represent that, because if you have got 16 bits, it will be 2 to the power 16 minus 1 is the value, which would be the last one positions. So let's start with the 16 address. 4, 4, 4, 4. That's the least value, the least address, or the first address location of the memory. And the last one is all ones, 16 bits. So these are the memory locations starting from, if you want to write in decimal, you say the 0, this will be 65,535. This is that position. If you want to write in decimal, right? That's the address locations of the memory. And each location would have a byte of value, which is the least significant bit, and that's the most significant bit. And that's your data. So if I look at the first position, first location of the memory, it has got all zeros. In hexadecimal form, I'll write as that's 4, 0, 0 is the value. So if you go to this is my address in hexadecimal, 0, 0, 0, 0, and the content is 0. Now you look at similar one. Let's look at that particular location. And what does that mean? That's 1, so you've got 1. That's a D, that's 1, that's D, that's F, and that should be C. So you'll have C, F, D1, that position. The memory content is, group them, 4 and 4. This is 9, that's 0. So it will be 0, 9 would be the memory content. Similarly, the last location, F, 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 F. So that's the last location. The memory content is going to be, that one is A from the table, that one is E, then you write as EA. So that's the answer for that example. If you are given a memory locations and its content, you should be able to rewrite them in the form of hexadecimal notation. But in the hardware, it will be stored like this, 0 and 1s. And you could assume every bit is represented by one D gate or one sequential logic, you could say. So you can count how many you need. Yeah? Okay, let's move on to the next one. Now we move on to the binary arithmetic again, which you have done before. But very quickly I'll run through this. When you add 0, 0, the output is 0. 0, 1 is 1. 1, 0 is 1. It's in binary, right? 1 plus 1 in binary is 1 0. 1 1 is 1 0 because in decimal 1 plus 1 is 2. The binary equivalent of 2 is 1 0. That means when you add them you get a 0 and a carry of 1. So from now onwards, remember, when you add 1 plus 1 in binary, you get 0 first and a carry then forward. So we use, in most of the computers, we'll use 8-bit arithmetic, 16-bit arithmetic, 32-bit arithmetic. Very big computers are 64-bit arithmetic. Now, I want you to add two 8-bit numbers shown here. And the result should be then, we need to write them as hexadecimal. Anyway, we start with binary first. We'll convert them later. Add them these two, least significant bit. This is a least significant bit. 0, 1, 0, 1. 1, 1, as I said to you, 0 and a carry 1. Add this one, 1, 1. Again, 0 and a carry 1. Then you add them this one, this and this will be 1, 1. And another 1, so it's 1, 1. So this 1. Then go back here to this one. It's 1, 0. Carry again. And you add them. You get the answer. So you can say in the fifth column, 1, 1 is 1, 0, plus 1 is 1, 1. So that's what in this column as that one. Just to show you an example. So you can add this one yourself. Now what's the hexadecimal equivalent of that? Is 1e. What's the hexadecimal equivalent of this 3, 4? That's 4, that's 3. And the results that you have now, if you look at the results now, and which is equivalent to, the results is equivalent to that one is 2, that one is 5. So the answer is 5, 2. Hexadecimal numbers are written as H there afterwards. So if you, this is 34, H stands for hexadecimal. And in some computers in a language, they could write H in the front and 34 afterwards. But this is the notation you'll be using for your microcontroller when you write in assembly. That's the format you'll be using. So there's nothing wrong. In some other computer will use H34. That means hexadecimal 34. Some places they'll do 34H. That's also the same. So letter H is used to signify hexadecimal numbers. Let's move on to the next one. Now we've got unsigned binary numbers. So you have two things that when you're adding, signed and unsigned. So let's look at unsigned number. When you add unsigned number, so I've got the smallest unsigned number in an 8-bit is, 0 zeros, that means hexadecimal 0, 0. So if I say this 8-bit number I have is an 8-bit number I have. Right? The smallest number is 0, 0, 0, 0, 0, 0, 0, 0. That's 0, 0, H. That's equivalent to. The highest number is 1, 1, 1, 1, 1, 1, 1, 1. So that's equivalent to F, F in H. So that's your equivalent. So now if you want to write this in decimal, and this is equal to 0 decimal, and that's equal to 255 decimal value. So that's unsigned. So if you have got an 8-bit number, the lowest value is 0, the highest value is 255. But in microcontroller or computer arithmetic, you need to use signed number. We'll come back to that in a minute. Now let's look at the unsigned binary numbers, which I have already explained. Now we add them with various problems that we'll face in a minute. So what we call is overflow. What is an overflow? When your computer cannot handle a number greater than certain things. So for example, if you have an 8-bit unsigned arithmetic, 255 is the maximum number you can represent. When you do an addition, if the number goes above 255, then what we say there's an overflow. Okay? So in an 8-bit arithmetic, if two unsigned numbers are added, and if the sum is greater than 255, an overflow will occur. So let's look at it. In this question, we've got two numbers. That is 158, that is 84. And we add them, adding the binary arithmetic that we have done earlier. So 0, and that's 1, 1, 0 this way. That 1 carry, 1 and 1, 0. And when you do this one, 1 and then a carry 1 here. And then it's carry 1 and carry 1. And when you add them, here's no carry, sorry, here's 1. When you add them, that's 1. There's no carry here. You can try it anyway, sorry. There's no carry in this part. So after this, 101, 101. Now if you look at it, this is 242, which is within the limit of 0 and 255. Therefore, the sum is between that, hence no overflow. Now take another number, which we are going to add, 158 and 100. If you add them, is 258. That means this is your value. That's 0, 255 with 8-bit arithmetic. 258 means that's outside here. So you cannot represent that in the 8-bit arithmetic. So what happens? So when you add them, you keep adding this one as with the normal adding principle, and then you will find there's another bit comes out. And if you see on the 9th column, if there's a bit, that means there's an overflow. You can see that if with the 8-bit arithmetic, only the lower 8 bits are used. We only take the lower 8 bits because it's an 8-bit arithmetic. And then sum is 6. Now if you work it out, this is 6 instead of 258. So in an 8-bit arithmetic, the answer is wrong. So what do we need to do? So if we were to consider, then you got to consider the 9th bit. And then if you convert this one, with the 9th bit, if you convert, this will become 258. So if overflow is taken into account, the answer is correct. But then we are no longer using 8-bit arithmetic. So if you use the 9th bit, this is the 9th bit, your process is only 8-bit and you can't use the 9th bit. So this is where problem comes into play. Overflow will come into play, and we need to be very careful when you are doing these additions to avoid overflow, or detect overflow in advance, or do other manipulation to avoid overflow. We'll come back to that later on, but just to understand that what is overflow. When you're trying to represent a number greater than its range, is overflow. So we now look at 1's and 2's complement arithmetic. 2's complement arithmetic is used to represent a negative number. So far we look at an unsigned number. Now we're going to look at signed number. So 2's complement representation is used to represent positive and negative numbers in a binary arithmetic. So let's look at what is 1's complement first. 1's complement is very simple. If you are given a 4-bit number, you invert every bit and you get 1's complement. That's the rule for 1's complement. So inverter, 0 go to 1, 1 go to 0, 0 goes to 1, 1 goes to 0. That's how you do inversion. Similarly, in this number, invert them. Every 0 goes to 1 here. So that's your 1's complement. Once you have got your 1's complement, if you add 1 to the least significant bit, you get 2's complement. So 1's complement number plus the 1 to the least significant bit, you add this to least significant bit, you get 2's complement. So find the 2's complement of this binary number. That's what the question is. So we write the number. So we write the number as, this one is our number, this one, and take the 1's complement. So every 1 is converted. Then add 1 to the least significant bit, and you do the addition now. 1, 0 is 1, 1, 1, 0, 1, 1, 1, and 0. So this is the 2's complement representation of this number. Now we'll come back to this in a minute and say, what does that mean, 2's complement? We'll go to the next slide. Okay? This is just the process of what is 1's complement, what's 2's complement of a number. So when we are doing positive and negative numbers, The table shows how positive and negative numbers are represented in 2's complement form. So we are going to have 4-bit representation, and we will have the most significant bit is 0 for a positive number, and the most significant bit is a 1 for a negative number. That's how we represent. So you will find in that case, if that is a positive, this is 7. That one is all zeros. This is positive and 1. And then these are the negative numbers. This means minus 1. This means yes, it's 1 here, so it means minus 8. So when using a 4-bit binary number, you can have plus 7, that many positive, and then minus 6 is the largest negative number. From there to there, minus 8 is the largest negative number. So the negative numbers in the table in 2's complement of a positive numbers except the last entry. So let's now start with a positive number, and how do you find the negative value of that? So I'm starting with the plus 5. And I want to find out minus 5. What is a minus 5 equivalent? Plus 5 is, as you know, the most significant bit will be 0. That is equivalent to 5. Now I take the 1's complement, add 1 to it. I get a number now. That is equivalent to minus 5. That's how you get the negative number. And after taking the 2's complement of this, we get that which represents the minus 5. So 2's complement representation of positive numbers always have the most significant bit 0, and the negative numbers always has the most significant 1. Now you have a question here. Some of you might say, okay, how do you know this is minus 8? That one, this one. How do we know? So we go and say, all right, let's take that number in this corner. Let's take that number 1, 0, 0, 0. We take the 2's complement of that. 2's complement, invert first. That's 1, 1, 1, 0. Then add 1 to it. That's how you do the 2's complement. 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1 plus 0 is 1. So this value now is equal to 8. So that's how you get the minus 8. Okay, so if you have a number in 2's complement, if you want to find the positive or negative of that, whatever number is, then you take the 2's complement of it, you will get what you want. Now 2's complement arithmetic, addition. Let's look at the addition of 2's complement. As long as positive and negative numbers are expressed in 2's complement representation, the results of addition is always correct. Right. Unless there's a range problem, we'll come back to that. So, add 2 numbers. This is an 8-bit arithmetic. So, if you have got an 8-bit arithmetic, so we need to know the range. If it's 8-bit arithmetic, the positive number that you can represent is 127, and the negative number you can represent 128. Remember, for a 4-bit arithmetic, the positive number is plus 7, the negative number, the least, is minus 8. Yeah, that's what we had earlier. And this is for 4-bit arithmetic. For 8-bit arithmetic, that's your 2's complement range. So when you do an addition, nothing should be in an 8-bit addition, we should have within the range. If it's within the range, you will have the answer, no problem. Let's add this one. Add 2 positive numbers. We know in decimal, if we add them, it's 97. 97 is going to be somewhere here. Yeah, 97 say. Therefore, the answer has to be correct when you add them. So you do the normal addition, keep adding. That's what you get. You convert them, you get 97. Now look at case 2, where we add a positive number and a negative number. Naturally, when you have positive and negative, when you add them in decimal, it's 57. Then I know it's going to be in this range, somewhere here. Therefore, it's not going to go wrong. So let me add this one as normal. You add this one as normal. You know the addition, and you will find there's a carry going to the 9th bit. You just, in 2's complement arithmetic, that carry, you just discard them. You just completely discard them. And the answer, discard the final carry because it's meaningless. In 8-bit 2's complement arithmetic, the answer will be within the 8-bit. So you can. Now let's look at 2 negative numbers. When you add these 2 negative numbers, you know naturally 44 and minus 74 is going to be 121. 121 is somewhere here, so it should be the correct answers. So let's do the addition. Minus 44 you know how to represent, 74 how to represent. And if you don't know how to represent, you write 44 and take the 2's complement of it, you get minus 44. Write 77 in binary and take 2's complement of it, you get that one. Now you do the addition, keep doing, and you see, you will find this carry 1 in the 9th column. You ignore that in 2's complement, you don't touch that. And you just then take this value, and you know most significant bit is 1, therefore it's a negative number, we know immediately. And take the 2's complement of that, you will get the positive equivalent, which is 128. Now you can say the most significant bit here is 0, therefore the number has to be positive. Here we see the most significant bit is 0, therefore the number is positive. So note in all 3 cases the results are correct. As long as the decimal sum is within that limit, within that range, then the results are correct. If you're trying to add 126 and 126, 226 numbers, it's outside the range, okay? We'll come back to that. So 2's complement arithmetic subtraction. How do you do in subtraction in 2's complement arithmetic? Which is easy, because the subtraction is that the subtrahend is taken away from the minuend. So what does that mean? In 2's complement, we can do subtraction as an addition. So if you are given 84 minus 22 in 2's complement, you rewrite them as 84 in 2's complement arithmetic plus, and in 2's complement you write minus 24, add them. So that's what you do. So you never do a subtraction, you just do addition always. So when you are dividing, when you are designing hardware inside the computer, you always design the adder, not a subtractor. And then you manipulate using the instruction whenever you want subtraction. You just do this process. So let's have a look at perform an 8-bit subtraction from 82 plus 15. So we start with the 82. We know it's a 4-bit number in binary. And decimal numbers are written as like that. And binary numbers, say 10104 bit, is written as like base 2. This is called base 10, which is base 2. And 15 is in base 10, this is binary. And what we need is subtraction, so we convert that into minus 15. So you take the 2's complement of that, and you will find that's minus 15. Now you do an addition. That's your original number. That's your negative number. You just keep doing the normal addition. You ignore the carry. That result has to be right. Because if you subtract 82 minus 15, you should get 67. 67 is a positive number, so the most significant bit has to be positive, 0, and then if you calculate the rest, it will be 67. Because this position is 64, this is 2 plus 1, so 64 plus 3 is 67. Now the last part in 2's complement arithmetic is the overflow, and you need to keep an eye in this when you are doing when you're writing a program in assembly or at a low level programming. If you are doing high level, you don't need to worry. High level is a C or C++ or Fortran or Pascal or various languages. You don't need to worry about it, even in MATLAB. Whereas at low level, which is what you will be writing in assembly to understand the full structure of the hardware, and then you need to keep an eye on overflow. Okay. So 8-bit arithmetic, if the sum is outside the range minus 128 plus 100, there will be an overflow. So here is our value, minus 128 is the lowest, 127 is the highest. Suppose the numbers are being added, 101 and 51, which is 151. And the sum is 101 and 51 and 152. When the sum is 152, so overflow occurs because it's outside this region. And overflow occurs into the most significant position. So what does that mean in 2's complement? Okay, have a look at here. That's your number, two numbers. When you add them, this is their results. But what happened is that you added two positive numbers in using 2's complement arithmetic. You ended up most significant bit as 1. Most significant bit 1 means a negative number. So you're saying the sign bit is a negative despite of the fact you add two positive numbers. Therefore, we have got overflow has produced an incorrect answer now. So that's how you check. When you add two numbers, and if two positive number provides a 1, then it's an overflow. Now you take two negative numbers, minus 84, 92, and you add them in decimal. We know it's minus 182. Minus 182 is outside here, so that's also overflow. So let's do then. Write down minus 84, minus 98, add them in the normal addition technique, and you suddenly see, you ignore the ninth one. In 2's complement, you don't touch the ninth column. Now you see here, when you add the two negative number, the most significant bit should have been is 1 to represent a negative number, but it's 0. So the sign bit, we call this a sign bit, is positive, despite of the fact that we added two negative number. That means an overflow has occurred. It cannot accommodate the range. That's how you check. You keep an eye on the most significant bit, and that's how you check whether overflow. So we must test for an overflow after each addition and subtraction by comparing the sign bits. Sign bits are the most significant bits. So if you take a 8-bit number, that's 4 bits there, 1, 2, 3, 4, and the most significant bit is called the sign bit. It tells you what sign it is, plus or minus. 0 means is positive number, 1 means negative number. So we keep an eye on this when you do the addition. That's what this part says. If you add a positive number and a negative number, you won't get overflow at all. Overflow will only occur if you add two positive numbers or two negative numbers. If you add one positive, one negative, you won't get overflow. Okay? So let's move on. This chapter 1b, I've got exercise which you can try them out. These are very valuable exercise for you to try them out and see whether you are able to get this answer. I would suggest you work individually and check among yourself, or work as a group. This doesn't matter. It's just to make sure that you have understood before we go to the next section. And there's some more exercise. Exercise 2 also deals with the arithmetic plus the 2's complement arithmetic as well, what we've done, and make sure that you understood, have done all these exercise before you go to the next chapter. Some of these examples were taken from these two books, and you don't need to purchase these books at all. And they're very basic examples. I just took them directly rather than me calculating them again. So it's useful, and there are plenty of material on the web, so you can always look through them.